Hello friends, and a very warm welcome again to the channel Derive. Today we'll derive the 4 equations of motion, first through a geometrical algebraic approach and then through calculus. So the 4 equations of motion are, first one being final velocity equals initial velocity plus the acceleration times the time. Second equation of motion is the displacement delta x equals the initial velocity times the time plus half acceleration t squared. Third equation of motion is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. And the last one is the displacement equals half t times the initial velocity plus the final velocity. So these are the 4 equations of motion. Let's start off with a geometrical, algebraic, derivation. First equation of motion, well, not that hard. We just start off with the definition of acceleration, which is the final velocity minus the initial velocity. So the difference in velocity divided by the time. This gives us, if we multiply both sides with t, at equals vf minus vi, which in turn, if we add vi to both sides, equals vf is vi plus at. And that's the first equation of motion derived. What about the second equation of motion? Well, for this one, we need to draw a diagram. Vt curve. So on the y-axis, we have the velocity, and on the x-axis, we have the time. So this is time. We start off with some initial velocity here, vi, and then we have a uniform acceleration. That is a constant acceleration. And after a time, we'll end up, time t, we'll end up at a velocity vf. And as you already know, the area under this vt curve, that's the distance traveled, or the displacement. How do we calculate the area under this curve? Well, first we have an obvious rectangle here comprised of vi with the height and t with the width. So delta x, the displacement, will be vi times t, the area of this rectangle here, plus the area of this triangle here, plus the height of this triangle being vf minus vi times the time divided by 2. But look at this, at is final velocity minus initial velocity. And that's the same expression as this one. So let's go ahead and replace this term with this term. And we will get delta x equals initial velocity times the time plus at squared, since we have a t there, divided by 2. That is the second equation of motion derived. Let's move on to the third equation of motion. For the third equation of motion, we will start off with the first equation of motion. Then we'll just go ahead and square it. So vf is vi plus at Let's square both sides. This will give us bf squared equals bi squared plus 2vi at plus a squared t squared. And what we're going to do now is that we will, from this expression, factor out 2a. This will give us bi squared plus 2a vit plus at squared divided by 2. And look at this now. What is this expression? Well, this expression, that is the second equation of motion. It's the same as this one. So it's the displacement. All of this is just the displacement. So let's replace this one with the displacement, which will give us vi squared plus 2 times the acceleration times the displacement. And this is the third equation of motion derived. Now let's move on to the fourth equation of motion. What we're going to do here is that we'll start off with the first equation of motion again through this expression. A equals Vf minus Vi divided by T. And then we'll take the second equation of motion, which is delta x equals Vit plus half At squared. Now let's go ahead and replace this expression with this expression here. Let's replace this expression with this one. What we'll get is Vit plus half Vf minus Vi divided by T squared. Let's develop this. Well, it's Vit plus half, let's put this within the parentheses, Vft minus Vit, which will give us Vit plus half Vft plus half minus half Vit, which will give us half Vit plus half Vft. Let's go ahead and factor out half t. This will give us times Vi plus Vf. And that is the fourth equation of motion derived. Okay, so now we've achieved this first part of the video by deriving the fourth equations of motion with the geometrical algebraic derivation. Let's move on to the calculus derivation of these equations. Well, once again, for the first equation, we'll start off with the definition of acceleration. Definition of acceleration, that is the difference in velocity over the difference in time, or the time derivative of velocity, if you so want, which would give us a dt equals dv. And this is a differential equation that we can solve pretty easily. Let's go ahead and integrate both sides. And the limit when it comes to time would be from time 0 to some time t. A dt equals, and the limit when it comes to velocity, position, acceleration would be some initial velocity to some final velocity here, dv. And since we don't have a time term here associated with the a, this expression will just be at. And since we don't have a term here as well, this expression will just be the difference between the two limits. So vf minus vi. And this, if we continue to develop it, we can move vi to this side. We'll get vf equals vi plus at. And this is the first equation of motion derived through calculus. Now let's move on to the second equation of motion. Second equation of motion, about the same principle. We start off with the definition of velocity. Definition of velocity is the change in distance over the change in time, or the time derivative of distance, if you so like, which gives us, just as up here, v dt equals dx. But before we go ahead and integrate this expression, what we want to do is that we want to take the v here and actually go ahead and replace it with the vf. So let's put this expression here. And what we'll end up with is vi plus at dt equals dx. And now we can go ahead and integrate both sides. Again, dt here, so we start off from a time 0, lower limit, to a time t. And on this side, we start off from an initial distance to a final distance here, xf. And so what's the primitive function of vi plus at? Well, it is vit plus at squared over 2, right? With the limit t and 0. And since we don't have, just as before, we don't have an x term here, so this integral will just be the difference between the upper and the lower limit, minus xi. And this is, of course, since the lower limit is 0, that's just vit plus at squared divided by 2 equals, and this is, well, that's just the displacement, right? Delta x, the final distance minus the initial distance. This, my friends, is the second equation of motion already provided here. So that's derived through calculus as well. Now let's move on to the third equation of motion. Third equation of motion will start off once again with both definitions. First, acceleration equals dv over dt, and then velocity equals dx over dt. This means that dt equals dv over a, but also on this side that dt equals dx over v. So this equals this, right? dv over a equals dx over v. Let's go ahead and cross multiplicate. This will give us v dv equals a dx. And this is a differential equation which we can solve again. Let's go ahead and integrate both sides again. So lower limit here, will be v initial, upper limit v final, v dv equals some initial distance here and some final distance here, upper limit a dx. And the primitive function of this one right here would of course be v squared over 2 vf vi. And since we don't have an x term here associated with the a, this expression would just be the difference between the upper and the lower limit multiplied by a. But remember once again that this term, that's just the displacement. That's just delta x, so we can write this as a times delta x. Let's go ahead and develop this. We'll get vf squared divided by 2 minus vi squared divided by 2 equals the acceleration times the displacement. Now let's multiply both sides with 2. We'll get vf squared minus vi squared equals 2a delta x. And then we can add both sides with vi squared and we'll get vf squared equals vi squared plus 2a delta x. And that is the third equation of motion. That, my dear friends, is how you derive the 3 first equations of motion. And for the 4th equation of motion, you can go back and look at the algebraic geometrical method for that one, where we start off with the first equation of motion and then replace the acceleration in the second equation of motion, and then we'll get the 4th equation of motion. And this one is probably the most powerful equation of motion, so to speak, because we combine the 2 equations, the 2 first equations of motion, and it is also the only one that is time independent, since we don't have a time term in this expression. Thank you for listening, and I hope I see you in the next video.